Hello and welcome to today's Laser Focus World webinar, How is the Ring Core Mode Revolutionizing Automotive Laser Welding, sponsored by MKS Ophir. I'm Justine Murphy with Laser Focus World, a division of Endeavor Business Media's Digital Infrastructure Group. We welcome your questions today during the webinar. They'll be addressed during a Q&A session following the main presentation. You can send them at any time by simply using the Ask a Question box and hitting send, and we'll answer as many of those as possible during that Q&A session. If you have any technical difficulties, just use that same Ask a Question box and our webinar team will be happy to assist you. And we recommend disabling any pop-up blocking software or extensions in your browser because sometimes these cause issues with the webinar player. And please be aware that today's presentation is being recorded and will be available on the Laser Focus World website within the next 24 hours. You'll be notified by email when that's ready. And now let's meet today's speaker, John McCauley, Senior Business Development Manager for MKS Ophir, who focuses on automotive and directed energy applications. Hello, John. It's great to have you with us. The floor is yours.
Thank you so much, Justine. I really appreciate the forum to talk. It is indeed always a pleasure to work with Laser Focus World and Endeavor Media. And I just want to start off by saying it's been par for the course, pleasure working with you all. And thank you so much for this forum to talk about this very important and hot topic in high power laser processing. So let's get into what we're going to talk about. Just a brief overview. Ophir, many of you recognize the name, but Ophir has kind of evolved over the years. We are now part of MKS Instruments. MKS Instruments prides itself on surrounding the workpiece. So it looks at a process and it provides the components, the knowledge, the expertise to surround that process and provide the components to help you be successful. Ophir is now part of that. We're part of the Photonic Solutions division, which includes Newport tables and instruments, spectrophysics lasers, and that group. So now we are part of MKS Instruments. So very happy to be part of it. We're talking about a historic problem that has been with joining of these highly reflective materials. Historically, near IR lasers have been used to produce reliable and deep welds at a relatively lower cost because it is a relatively mature technology. But there is a problem with there historically has been a problem with using near IR lasers with these highly reflective materials. And we're talking about copper, we're talking about aluminum, some brass joining applications. And the historic problem with using near IR lasers is that there historically has been spatter and porosity. Well, this translates into lower quality welds. The aesthetics of the weld are not pleasing. Some of the applications where there just absolutely cannot be any spatter due to the component being welding, that's been problematic. Advance a few years, visible lasers came on the scene, the green and blue lasers, which, if you look at this graph right here, they do have a higher absorption into these materials that we're talking about at these wavelengths. So that is certainly a positive. However, these wavelengths are really, as it is right now, they're limited in the depths of the welds that they can produce. And since they are a relatively immature technology, they do come with a higher cost. So here, these are some of the limitations that these visible lasers have. So the infrared lasers on one hand, they're relatively inexpensive. They do have produced reliable welds, but at these highly reflective materials, they're problematic. The visible lasers, on the other hand, higher absorption, but they're limited in their applications. So laser applications engineers have come up with a solution. And that's what we're going to be talking about today. We're going to be talking about this shape, the ring core mode. So we'll talk about today what we do know about the ring core mode and where this beam shape is being applied. Because we are talking about laser welding, we are using very high power lasers, so multiple kilowatt laser powers. So sorry, that's not a word. Regardless of the laser shape that you're using, whether it be a ring core mode or just a traditional spot laser, you working with a higher power laser. So what do these ring core lasers have in common with other high power lasers? And then we also want to talk about what unique performance characteristics these ring core lasers have, and also how they can be measured. How can we measure these lasers in order to ensure that we do have a relatively stable process over time? But specifically, we're talking about these ring core lasers. And then when we talk about measurement, we ultimately have the end goal of taking your process, regardless of how you're using the laser. We want to take it and we want to ensure that we are best utilizing this laser shape through measurement, through verifying that the laser is performing consistent over time. So that's kind of the agenda for our talk today. So let's talk a little bit about this ring core shape. Now, I will, on the front end of this webinar, I am going to freely admit to you that I am not an expert in laser applications. So I'm going to talk about the application of this laser in very general terms, and I'll leave it up to you to dig deeper a little bit into how this laser is being applied, and talking to those laser applications experts on where you can use those lasers. But at a very high level, what this laser shape does, it is you can see from these two images, you see a 2D and a 3D view of this laser, which was taken by myself. You've got a ring that surrounds a core, and then this ring you can see is at a relatively lower intensity of light. And it is used basically for conditioning the metal and getting it ready for the weld. So it's applying some amount of heat into the material and conditioning it for the actual weld. Now the core is what provides the weld penetration. So you've got the best of both worlds. You've got basically two lasers that you're using here that is preconditioning the laser, or I'm sorry, preconditioning the material, and then coming behind it and producing that high quality deep weld. These lasers are both single mode and multi-mode. So you've got the single mode lasers that are used for smaller precision welds, where you do need high quality, where you do need low spatter. You've got some battery applications. You've got a lot of battery components that you just simply cannot have any spatter. So that there certainly is a strength there. And then the multi-mode lasers, which are for those relatively faster, deep penetrating welds. So they come in both single and multi-mode. But the end result, and I want to thank Trump for this image that they've got on their website, because it really is a good illustration of what the laser is actually doing with the material. The end result is you've got a relatively stable keyhole. It is a spatter-free weld, or just very minimal spatter at the very least. This translates into a very higher quality finish. You've got less porosity because you've got a stable keyhole, and it translates into a higher quality weld. Now, another disclaimer that I want to put out there is that there are a lot of different laser source manufacturers who are utilizing this technology. I'm not really here today to tout or to promote any one laser company over another. I just wanted to give the audience an idea of which laser companies. There are probably more, but these are the ones that I personally have worked with over the years. They've been Ophir customers over the years. They are all fantastic companies to work for. I will say that the technology behind generating this particular laser shape, it is a little bit different. The companies and the products generate the beam a little bit differently. Some of them use a single laser generator with two fibers. Some of them use two generators for the ring, one for the ring, one for the core. And it really just comes down to how the company has decided to generate this laser shape. and it's really up to the customer to find out which laser generator is best for you. But just know that this really is a revolutionary beam shape, and it is being used very widely with respect to joining these dissimilar and very highly reflective materials. I like this graphic. IPG has got this on their website, so you can go and see it. It's got a side-by-side graphic of what the weld is doing in slow motion between a traditional historic single beam laser. You can see that you've got a lot of spatter. You can visualize the keyhole being very unstable. And the end result is just an aesthetically not pleasing weld, versus what they call the adjustable mode beam laser, or the AMB laser. Very stable keyhole, very stable weld. So that's the kind of result that you can expect from utilizing this beam shape. All right, so where is this beam shape being used? Like we've already talked about, welding of highly reflective metals. You've got the copper, the aluminum, the brass in some cases, and it's where you need a weld, where weld spatter and weld quality are concerned. So you may have an application or a component going into a larger system where you absolutely have to have a high quality weld. You absolutely have to have a spatter free weld. So that's where it's being used. Welding dissimilar metals as well. So for instance, copper to aluminum, aluminum to copper. This shape is being used with respect to welding dissimilar metals. And then there are also some cutting and drilling applications. So some higher power density applications where the laser shape is concerned, it's being used there as well. And then one company is using it for laser powder bed fusions as well. So as you well know, if you work in additive manufacturing, the porosity of the build is certainly a concern when it comes to analyzing or ensuring the part integrity. If you do have porosity, you're going to have problems with the strength of the parts being used. So this laser shape is being used in some laser powder bed fusion applications as well. All right, and I messed up my my animations here, so I'll just show you all of them. And so this laser shape that's got some common concerns that are shared with all high-powered lasers. So in effect, you are using high-powered, you're generating larger amounts of photons, right? So it's kind of obvious, but you're using higher amounts of photons, higher amounts of light, and that's going to translate into higher power densities. Well, with these higher power densities, it's going to end result in a couple of different problems. One, laser safety is obviously more of a factor. Same with the ring core mode laser as it is with any high power lasers. You need to take precautions to protect your eyes, to protect your skin. So those are common with all all high power laser. But really what we're talking about in this webinar is because you're using high power laser, it is going to be relatively tougher on the components within the laser system. Laser system is made up of parts, physical matter. They are going to degrade. They are going to be degrade a little bit quicker because of just the amount of photons that's passing through them that's within the system. So that needs to be considered as well. These lasers, because they are higher power lasers, because they are being used for welding, for cutting, for drilling, these are relatively harsh operating environments. So greater precautions need to be taken to protect the laser components from process debris, from just general these general dirty environments. And then, of course, since we're ultimately going to be talking about measuring these lasers and ensuring that we have high quality laser processes, there are also some additional measurement challenges that need to be taken. So for instance, water-cooled sensors, because we're talking about multiple kilowatt lasers. You'll oftentimes have to use water-cooled sensors in order to measure these lasers, just as an example. Now, there are some characteristics that are relatively unique to this laser source. A couple of points I will freely admit that I just kind of speculated on, and I'll point those out. But in effect, you're using with this beam shape, you've got two lasers instead of one. You've got one laser that's preconditioning the material, and you've got another laser that has its function, which is joining the material. So you're in effect, you're treating it like two lasers that are operating at the same time, that have two very different sets of performance characteristics. You've got the ring, which is a relatively larger beam size, a relatively lower intensity, and hopefully you see that with these two images, both the 2D and the 3D images. The ring is just operating at a lower intensity. It may be of a higher power, but it's at a lower power density. Versus the core, where you have a relatively smaller spot size, which is going to result in a relatively higher power density. Two very different power densities, two very different results in how this laser is processing the material. That's going to come into play when we talk later in the webinar about power density, because it's a really good illustration of that fact. This I guessed. Because we're using two different lasers, I would imagine that people who are developing applications with this laser shape probably has to put in greater time into the development of the application. And again, I'm just kind of speculating on that, but I would imagine that's probably an additional challenge with using this laser shape. Again, I kind of guessed on this. It's just really kind of speculation, but I would imagine that there's probably some increased care and possibly some increased costs with maintaining a system like this, with developing the system that surrounds this laser shape. Again, I'm just guessing on that point, but I just kind of anticipated that's the case. But when it comes to measuring the performance of these lasers, these two lasers, the ring and the core, they've got independent laser power measurements, and they've also got independent beam profiling measurements. Two very different sets of characteristics for very different results in what these two shapes actually do to the material being processed. All right, so let's talk about a little bit more into my comfort zone. I'm a laser measurement expert, and so I would like to leave you with some thoughts on some meaningful laser parameters to measure on these ring core lasers. So what, in general, when talking about the operation and the maintenance of any laser, what laser measurements are meaningful? Number one, I think everybody who works with lasers can agree that output power or energy at the work site is very important to understand when it comes to operating and maintaining your laser. The amount of light that's inputting into the material is a very important characteristic to understand. But that's not the end of the story. There's also the beam profile. The beam profile is going to tell you the beam size. It's going to tell you the geometry of the beam, what the shape is. And since we are talking about a very unique shape that's being applied here, knowing what that beam shape looks like and knowing what it looks like specifically at focus is very important to understand with maintaining a consistent process with this laser shape. The laser caustic, and we're talking about what is happening at focus and around focus. So the Rayleigh length, which loosely defined is the amount of usable laser added around focus. There's a band in which you can ensure that the power density is going to remain relatively consistent. The divergence angle of that laser is very important in some stages of the laser life cycle, as well as the M squared, or the beam parameter product, which ultimately defines what the quality of that laser is. And then the laser spot location. So you've got not only the XY location, ensuring that the laser is consistent in its position onto the weld with respect to X and Y, but also the focus shift, which is the Z location. Do you have some kind of thermal effect on the laser system that's causing the focus spot to drift towards the laser system, which is going to result in a larger spot size that's being applied to the material. So knowing all of these laser characteristics is very important, not only when developing the application with these lasers, but also when you put the laser into production and you have a longer term of the laser life cycle and a longer term responsibility of maintaining laser consistency with respect to the process that it's involved with. All right, so power density. Power density is a term that I've used a few times during this webinar so far, and I just want to make sure that everybody understands this idea of power density, because it is very important to understand regardless of what laser you're using. So at a very high level definition, it is a measurement, or it is a set of characteristics that defines the overall laser's performance. Each material will have a laser power density at which the desired result is achieved. So let's take laser annealing, which is just a change of the surface properties of a material. It's just changing the color or just adding a little bit of heat to the material, versus laser cutting, right? Laser annealing is going to you could take the same laser, but with a lower power density, you can achieve the annealing of the laser. You have to have an extremely high power density in order to blast material away to result in a stable cut of that material. So hopefully that illustrates the importance of knowing what your laser power density is with respect to the process. Now, the power density is made up of this expression, usually expressed in watts per centimeter squared, or some variation of watts, like megawatts per centimeter squared, where you're talking about kilowatt lasers. But it's effectively, it's the amount of light that you're applying to the material, which is represented by the top of this expression, versus the beam size that the laser is focusing down to. Any change in either one of these characteristics of the laser will change the power density. If you have a drop in laser power, it's going to decrease the power density, for example. What changes power density? It's a really good thing to discuss. Like I mentioned earlier, things happen to laser components that will affect its performance. Because these lasers are operating in relatively dirty, relatively harsh environments, they are more susceptible to having process debris being collected on optics and just changing the integrity of the optics. I'm really specifically interested in these two bottom pictures. These are pictures that I've taken over the years of contaminated and defect optics. But these two bottom ones are pictures of cover glass that have had some kind of contamination on them that the laser has effectively burned onto the surface. Well, what's happening in that case? Number one, your laser light is being absorbed by this defect, so you are having some, albeit slight, reduction in laser power. It is decreasing, but also what's happening is it's changing the property of this cover glass. It's changing it from a cover glass, which is not supposed to really affect the performance of the laser. It is changing into a lens because it is absorbing some of the laser light. It's changing it into a lens, and what's happening is the position of the focus spot is drifting off of where it is supposed to be. Again, we're talking about power density. When there's a change in laser power, when there's a change in the beam size being applied, the overall power density is going to change, and it's going to ultimately cause your laser process to change, possibly out of its designed parameters. All right, so looking at it another way, you're a laser operator. You come in 8 o'clock in the morning. You load up the parameters in your laser process, and you start to go. Right. Well, that's not always going to result in the programmed power that you program your laser in is not always going to result in the process performance, and that's what we're talking about. We're talking about things that happen to the laser that can change its power density and therefore change the process in which the laser is being used. You can reduce, your power can be reduced. So you program 4 kilowatts into the laser, but because of some kind of defect in an optic or something else happening with the laser system, it could translate into 3.5 kilowatts into the process, which decreases the power density. You could have some kind of focus shift on the laser system, which increases the beam size, which will change your power density as well. So let's look at this crude cartoon here. Look at the example of component degradation causing gradual decrease in laser power. Day one, you've got a 2 kilowatt process. You've got the laser focusing down to the material. Everything is great. 100 days later, for whatever reason, you take a laser power reading and you've got 1.7 kilowatts. What's that doing to the power density? It's decreasing the amount of light that's being applied to the process, which results in an overall decrease of the power density and a loss of efficiency of that particular laser system. Measuring laser power by Ophir is done at several different approaches. I kind of laid it out with 4 different products here just to kind of illustrate the 4 kind of categories that we have with respect to measuring laser power. The products on the left are pulse to power. So basically you pulse the laser for a split second and it returns a single value of how much power was in that particular pulse of light. On the right here is the water-cooled system. So you can fire the laser as long as you like. You can see trends of laser power over time. I might make the argument that this is probably a better way of measuring your laser performance, and I'll talk about that here in a second. The 2 top products are intended for integration into a laser cell, so you permanently install it into the laser cell, take periodic measurements, where the 2 bottom ones are more intended to be used for like a maintenance scenario. So where you store it away, you bring it out as needed, take a measurement on the laser, take actions if needed, and then store the product away. I want to talk specifically about the IPM for a second. This is Ophir's product called the Industrial Power Meter. You see a picture of it installed in an automotive laser cell. It really is, again, it's designed for integration into a laser machine. It's used for these near IR lasers that we're talking about and CO2 lasers. It measures up to 12 kilowatts of laser power continuously because it is water cooled. It's also got a feature on there. It's a quick go, no go. So you fire the laser just for a short amount of time and it will tell you if the laser light is present or not. A customer of ours asked that for that specific feature. It's an Ethernet IP or Profinet depending on your your logical environment, and it is a very rugged design. It's IP rated connection, so it is intended for long-term integration. Again, we're talking about measuring laser power, verifying that the top of that equation is consistent over time. The Ophir Helios Pro is a new product that I did want to introduce to this audience. It's a variation of our Helios product, but we did add the visible wavelengths, so it measures both visible and near IR wavelengths. It's a quick single data point. It's intended to be integrated into the machine. It also measures up to 12 kilowatts of laser power just in that short burst. Ethernet IP communication. There's also a Profinet version if you're Europe or if you're operating in that environment, and it's got again, it's got the rugged design with the IP rated connections, as you can see. I like to show this graph because it really is a good illustration of why I think it's important to take time-based measurements. This was on an older CO2 laser, and this particular customer had a very inconsistent cut with their sheet metal, and they called us in to troubleshoot. You can see that at the 5.2 kilowatt setting, the laser started off stabilizing at roughly 3.6 kilowatts or so. It was bouncing around for several seconds, and then ultimately around 45, 50 seconds or so, it stabilized at that 5.2 kilowatts. Well, if you are using this laser for cutting, you're making these long cuts, you can visualize what's happening to the cut, right? You're starting off with a very, very unstable cut. You don't really know what's going on, and then it's finally stabilizing towards the end of the cut. This particular laser, it was a CO2 laser. It had a leaky resonator, and I want to say that it was helium that was leaking. But because of that helium leak, it was causing a very unstable cut. So this graph is great for illustrating the point, but that I think is very important to not only have that single data point, but also to take those time-based measurements. Okay. Let's move to the bottom of the equation, and I want to illustrate this point. Same laser. You've got 2 kilowatts being programmed. You've got it processing some material. And when the laser turns on, everything is fine, but you've got some kind of thermal effect on a contaminated optic that's causing some spot size change or location. So you've got a spot size that it's intended to be when you start off, and then some seconds later, 5-10 seconds later, you've got some kind of focus shift on your laser system. What's that happening at the process? At the process, the laser spot size is increasing. So the laser spot size is increasing. Well, using simple math, if your denominator increases, what does that do to the overall expression? It decreases the overall power density in this case. Here are some, since we're talking about ring core lasers, let's bring it back. This is kind of where the rubber meets the road in this entire this entire webinar. I'm about halfway into it. I finally got there. So here are some beam profiles on this ring mode laser. This particular laser is a coherent FL 10,000 ARM laser. ARM stands for adjustable ring mode. Very, very nice laser system. I got to measure this laser a couple of different times at the KUKA lab in Sterling Heights, Michigan. Some of you may have been there to do some application work, but got the chance to do some measurements on this laser. Very, very nice laser, very stable laser. So rest assured that you're getting some good results from the guys in the apps lab at KUKA. So here are some B profiles on the left. You see both the 1D, the 2D, and the 3D profiles all in one shot there, so you can kind of get an idea of what this laser looks like. There are a couple of different beam profiling approaches that Ophir uses. One is the camera-based method, and one is the Rayleigh scatter method, and I'll talk about both of those here in a second. They both have their strengths and their weaknesses, and that's why I kind of wanted to talk about these and kind of make you aware of the technology that's used to capture images on this laser. The beam gauge product, beam gauge is an Ophir product, consists of an attenuation device that reads up to 5 kilowatts of laser power and reduces it down to nanowatts to view beam sizes down to about 37 microns in diameter. It does view the focus spot size. It does view the ellipticity of the roundness. This image right here, the blue and orange and yellow devices or image here is what you can typically see from a beam gauge system. It also gives you the beam stability. Since it is looking at the beam on an XY plane, it will tell you if the beam is traveling around so that you can ensure that it remains consistent with the location of your weld. And then also, because it is dumping about 99.99% of the beam, you can put a power meter underneath and collect it, use it as a beam dump. or you can collect the absolute power and calculate power density. These devices also, you can calculate a divergence angle and m² if you move it through the waste. It's also got that feature as well. Again, we're talking about the power density, and we're talking about verifying that that spot size is what it's designed to be, and that it is consistent in its location. Here are some additional images that I took on this ring core laser. Excuse me. At the KUKA lab. The top left is the core at 500 watts. The top right is the ring at 4 kilowatts, and you see that the intensity between those two lasers at the top are roughly the same. You're getting into the yellow, so it indicates about the same power density. But you notice, obviously, the ring is of a larger size. So since you are at 4 kilowatts, where the core is at only 500 watts, about an eighth of the power level, you get the same power density between these two beam shapes. Additionally, at the bottom, you've got some shapes that further illustrate this idea of power density. You've got the core at 1 kilowatt. You've got the ring at 2.2 kilowatts. You see the core is obviously a smaller beam size, and even though it's at a smaller power level, you get a much higher intensity, much higher power density. And this bottom right image, you've got the core at 500 watts. You've got the ring at 3.5 kilowatts. You've got, roughly the same intensity. The core is a little bit more intense, or a little bit higher in power density, even though it is at a smaller, or a lower laser power. All right, so just to talk, I'm just going to talk real briefly about this, about the approach to beam profiling. While using the LBS 300 or a beam gauge device like this, your first step is to attenuate the beam. It needs to be at a power level that's suitable for the camera. Then it needs to be sized correctly. It's very possible that your beam size may be too large or too small for the resolution of the camera, or too large to fit on the camera imager. So there may be some sizing that you may need to do. Once the beam is attenuated with respect to power and sized properly, that's when you image the beam, and you take that image and you send it to the software for analysis. So that's basically the general approach to beam profiling. Here's a device that called the Beam Peak that we introduced fairly recently. It is an all-in-one beam profiling and power measurement product. It's got a silicon CMOS camera with a beam splitter assembly inside. It is limited to about 1 kilowatt because it is convection cooled. There is no external cooling, which is nice. There is one single cable that runs to it, basically for the communication, but there is no there are no other cooling wires, or gas purge or anything like that. As far as key measurements that it measures, again, it measures laser power, and these are all real-time measurements. It measures real-time laser power, real-time laser focus spot size and shape. It does calculate power density automatically. It gives you an idea of what the beam geometry is going to do. And then this particular device, it does have a feature in the software where you can run through focus and take a manual m² measurement as well. It does have that feature in the software, so I thought I would make that available to you. Okay, so we talked about the beam gauge system and the basically the XY slice of what the beam is doing. Let's move on to the Rayleigh scatter method, which is a device called the Beam Watch, the Ophir Beam Watch. Also on this coherent arm laser in the KUKA lab, same laser. So you get some apples to apples comparisons of what you might get from this particular laser with respect to the beam geometry and what's happening at focus. So little tough to tell from the picture here, so I'm putting a box around, right now I'm putting a box around the laser head, and now I'm putting a box around the beam analyzer, which is the Beam Watch. It is a completely pass-through device. There is no upper limit. It's a solid state device, and it views the beam caustic real time. So it can give you some very useful characteristics about what your laser is doing. So I'm going to present what the laser is visually, since it's an invisible tool. It's kind of tough to see, but you can see from this graphic here that the laser is focusing down into the device and then diverging again into a beam dump underneath the beam watch. And so you can see at the left of the screen, you can see that the laser is focusing down. It's analyzing the laser at focus, and then it's diverging again, and it's giving you some characteristics about what this laser is doing. Beam watch, there's two different versions of the beam watch. There's one for beam sizes greater than 130 micron in spot size. It is specifically designed for near IR wavelengths, 900 to 1100 nanometers. And then there's the Beam Watch Plus, which we introduced just recently. It does add the visible wavelengths, so those green and blue lasers, it will measure those. And those go down to more suitable for those single mode lasers at 45 microns and above. As far as the measurements that we get from the beam watch, absolute position measurement. So if you need to verify the absolute position of your focus spot periodically, this is the device to do that. And then it also gives you relative time-based measurements of your focus spot size, so you can track the beam size and the spot location in real time. It will also give you real-time caustic measurements, so your Rayleigh length, your divergence angle, your M squared and beam parameter products. As soon as you turn the laser on, you are getting measurements of all those very important laser characteristics. And then also, if you integrate it with a power meter, you can get a power density measurement as well. Again, we're talking about the bottom of the power density equation, verifying that your laser spot size is consistent and not drifting or anything, which causes the spot size to increase at the bottom of the power density equation. Let's look at this ring core laser, this adjustable ring mode laser, and analyze just its core and just its ring. Now, I'm going to admit that this device, the Beam Watch device, if you're interested in beam geometry, this probably isn't the device that is for you. It is the real strength of the Beam Watch is tracking focus spot location and tracking any changes to that, as well as instantaneous real-time M squared and caustic measurements. But if you want to see what the geometry of the beam looks like, you're probably better off going with a camera-based system. But having said that, this is what the geometry measurements that you can expect from the Beam Watch. You see at the left here, basically the slice through the spot, and you see what the core may look like. It's very intense in the middle, and it drifts down. It looks like a very Gaussian type shape. Compare that to the ring. This is the ring only at 4 kilowatts. You can kind of see the geometry of what's going on at focus. But again, this laser really isn't that. I'm sorry, this measurement device is not. That's not really the strength of this particular device. There are a couple of variations of the Beam Watch product. This particular product line is called the Beam Watch Integrated, and this is a device that is a beam profile and a beam power measurement device all in one device. So you can measure laser power and those laser characteristics that I just talked about. Again, up to 12 kilowatts of laser power. It is an industrial design with IP-rated connections. It's available in Ethernet IP or Profinet. And then it's also got an actuated shutter, which protects the internals of the Beam Watch Integrated when not in use. It can be mounted vertically, mounted horizontally. It's a solid state device, so it doesn't really matter the orientation of the device. As far as the operation of the Beam Watch Integrated, just wanted to make you aware of this. If you look at the Beam Watch itself and then the power measurement components of it, and then say you're measuring a laser head that's connected to a robot, you fire the laser, it focuses down into the Beam Watch, and then it diverges again to take the power measurement. Those two sets of measurements are sent to an onboard PLC. The onboard PLC kind of analyzes what's going on with the measurements that we've set up ahead of time, and it'll tell you, yes, you're ready to go. It'll give you a caution. It'll give you a no-go. Basically just depends on how you want to set it up, and you can use it for process control if you wish. So those measurements, those results are then sent back to the robot for deciding what to do with those measurements. All right. So as far as closing thoughts go, we're wrapping up at the end of the this webinar. There is no doubt at all that the ring core laser beam shape is revolutionizing the processing of materials traditionally difficult to process. Beam shaping has been around for decades, and there's been a lot of work done with different beam shapes, but there's no doubt that this particular beam shape is really making a difference and producing some very, very high quality welds, specifically with those materials that are relatively difficult to join. This unique beam shape has many characteristics common with other high power lasers with additional unique characteristics. So it does use a lot of photons. It does use those multi-kilowatt sources. So with respect to that, it does have some things common with other high power lasers, but it also has, as we talked about, some very unique characteristics as well. Laser power density, as we talked about, is really just simply the definition of how a laser interacts with the process. It's really very important for a laser operator to at least understand that laser, it's not just laser power that you change to change how the laser is behaving. It's also the spot size and understanding how those two laser characteristics are in relationship with each other and how that affects the power density is really the key to the laser operator ensuring that there's consistency with respect to the process over time. And then I'll make the argument that measuring, analyzing, understanding, and keeping consistent the laser characteristics that affect power density, at least affect power density, is how you can know for sure that you will have a long-term healthy laser process, not only on the ring core laser, but any high power laser, really effectively any laser. It's really important to know how your laser is behaving to ensure that you have a consistent laser process. So Justine, if you are still with me, we've got about 14 minutes or so for a Q&A, and I guess we'll just open the floor to anybody who has questions.
Great, fantastic. Thank you so much. And now, like you said, let's move into the Q&A. As I mentioned earlier, if you'd like to submit a question, just use that Ask a Question box. And we do have some in here already, which is great. So let's jump in.
All right.
For laser power and the beam profile, can you analyze the core and the ring independently?
Okay, yes, this is a good question. This is actually a question that we've discussed internally at Ophir as possibly being important to laser users who are using this beam shape. The answer is, while the ring and the core are fired simultaneously, it is really impossible for a power meter to know how much is going to the ring and how much is going to the core, right? Because all it sees is laser light. And so you're firing the laser and it just sees a power meter. So it is going to be a combined power measurement. Now, with the beam profiling currently as it is, it's relatively difficult to analyze the core and the ring separately. However, we have talked at Ophir about adding some kind of feature where that could happen. But as it is right now, you would have to fire the ring without the core, and then the core without the ring, in order to get analysis of those two lasers, to know how each component of the laser is operating independently of each other.
Okay. You discussed pulse to power versus the water-cooled power meters, and this person thanks you for explaining the difference. Which would you recommend for measuring these types of lasers?
Yeah, that's a really good question. The bottom line is you can use either the pulse to power or the water-cooled systems to analyze laser power for these lasers. But Personally, I recommend the water-cooled systems just because, number one, you can use it for a very quick measurement. You don't have to fire the laser for several seconds. So I know that when they're utilized in production environments, um, time is a factor. So you oftentimes don't have a lot of time in order to take the measurements. I realize that. And I do know that, with these water cooled systems, you oftentimes have to fire it for several seconds in order to get a stable reading. But in the end, to get that, if you remember that, let me back up to that graph that I had. If you remember this graph of what laser power is doing over time, what you want to see is a laser power that comes up immediately to where you are programming it and hang out there for several seconds. That's the graph that you want to see, right? Because you know that the laser power is putting the programmed laser power at the process, and you can ensure that even more so that you have a healthy laser. Well, you can't really do that with a pulse to power system because you're firing it for just a second or a split second, and you're getting one single number back, right? So although the pulse to power is a good indicator, it's good for tracking laser consistency over long periods of time. If you do have a problem with your laser, it's really not very good for troubleshooting what your laser is doing in that time. Also, beam profile. If we talked about focus shift and what focus shift is doing. That's really not going to be reflected in either way in your laser power. So whether it's a pulse to power or a water cooled system, if you do have focus shift on your system, that's not going to be reflected in the laser power. So you may get a nice stable laser system, but still have problems with your laser. If that's the case, it may be a focus shift issue, may be some kind of component issue. But hopefully that answers that question.
Okay. Are your measurement devices used to measure the laser during the processing, or are they used between processes?
Okay, yes, very, very good question. It's one that we get common. These devices are used to measure the laser between part runs. It's used. Our products are used to measure the laser while the laser is not processing. It's really just intended to be a snapshot of how your laser is performing at that point in time. There are systems out there that are process monitors, not only laser power, but also vision systems that look at the keyhole, for instance. There are a lot of analysis that goes on during the process. We just don't make the products to do that, and that's simply for one reason. If something is going to be wrong with your laser system with respect to the location of the spot size or the laser power, it is likely going to happen upstream of the components that's closest to the process. So, for instance, if you have a focus shift situation, that's more than likely going to be because of a contaminated laser optic that's close to the system. An in-process monitor is not going to measure the laser power, taking into consideration that those optics that are closest to the system. So, that's kind of why we steer towards an absolute measurement of the entire system with our products.
Okay. Well, unfortunately, we are nearly out of time. Any questions we weren't able to get to today will be addressed directly later via email. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank John McCauley for such a great presentation, MKS Ophir for sponsoring today's webinar, and of course, all of you too for joining us. Enjoy the rest of your day.